Okay, to begin, let's take a look at the water cycle. And the water cycle is the pathway that water takes over the surface and sometimes below the surface of our planet. It's kind of that pathway of fresh water. Now, most water is going to start in a bank, and the biggest bank we have is going to be the oceans. And this is just an area for storage. From there, we see that it evaporates out up into the atmosphere. And as it does so and gets cooler the higher it goes, we get condensation. And condensation is going to form clouds. And those clouds are going to continue to build. And if they get too much water inside of the clouds, then we see what we call precipitation. And that's water falling from these clouds. Now, there's four types of precipitation: rain, snow, sleet, and hail. And that gets it from the atmosphere back out and down. Once it gets to the surface, it has two different pathways. It can run over the surface, which we call surface runoff, or it can permeate through into and become groundwater, and then this groundwater can then flow as well back to the ocean or back to the bank. Now, one of the other ways that we kind of see that we don't talk about too much is this transpiration, and that's going to be that water that's released from plants. So you can see that we have all this water on the ground or trapped in plants. It'll evaporate or transpirate into the atmosphere. From there, it precipitates down, and the whole cycle continues, and that's why we call it a water cycle. Okay, so this unit's going to talk about how streams and moving water have the ability to move stuff. And we talk about it as being streams, as this moving water, because that's where the concentration of most of the moving water is. While we do have some erosion from this rain and runoff and from snowmelt, most of it's going to travel into streams. When it gets into the streams, then you have a stronger force that's able to move more sediment and move more materials. And there's a couple things that affect stream flow. The shape of the stream is going to affect it. If we take a look at this one here, we'll notice it's a straight stream flowing down. You can see the maximum velocity is here, and you kind of have a uniform as it spreads out. So it's kind of like equally as the further you get from that high point. If we have a bend in the bank here, where you can see this bend here, then what we notice is that the maximum velocity is still kind of in the same location, but we notice that it's kind of going to be a little more speedy on the outside of the bend, and that's going to cause a little more erosion on that side of the stream. Now, a couple other things that are going to affect stream flow and how fast it's going would be the characteristics of the channel. And that's quite simply, what's the bottom like? Is it going to be a smooth bottom like you see in the pictures? Then you're going to get nice, even stream flow. Versus if there's a lot of big boulders and things down here, then you're going to see it's going to have to move its way around there. Is it natural? Is it going to be dirt, rocks, sand, or is it going to be concrete? Concrete's going to flow a little faster, but there's less erosion on that concrete because it's a man-made surface. Also, how steep it is. You'll notice that in the mountains here, we'll see it's a lot steeper than it is here down on the plains. So we can see that that's going to affect steam flow, and that'll ultimately also affect how much it's going to erode and how much it's going to carry stuff away. Discharge would be how big it is, and then we already mentioned urbanization. So stream flow is going to determine how much it can erode away and how much it can carry away, and that's one thing that I want you to keep in mind as you're going through the lessons. Now, there's significant changes from being upstream and downstream. Upstream is what we call the headwaters, and that's where the streams form. At the headwaters, we tend to have this high gradient, so it tends to be steep, but we're going to have a little bit of water in there. So you're only getting a little bit of this water formation, so you're going to have a little bit of water traveling downhill really quickly. Conversely, when we get to the mouth of the stream, or the downstream part, then what we notice is that this gradient is kind of leveled off a little bit. So if we drew a profile, we'd start in the mountains, and then it kind of levels off as it goes down into the ocean. So you can see that the steep gradient here in the headwaters is going to allow that water to appear to be moving really fast, whereas down here you have a very slight gradient, a very gentle gradient going there, but we generally will have more water in those down here closer to the mouth, because if you look here, you can see all of these little tributaries that are all feeding into this one stream or river right there. Okay, the last concept that they want to go through in this unit is going to talk about base level. And base level is quite simply where it's going to be, the deepest that that stream can cut through. When you have a new stream cutting through, you're going to see that it's going to be cutting through deep valleys here, very V-shaped valleys going on here, and the base level is going to be down here. For most streams, the base level is going to be the ocean. It's going to be sea level because once water gets down there, it's in the ocean. You can't have it dip down below and then flow uphill. Water always flows downhill, and the lowest it can flow would be sea level. Now, for some streams, it might be a little bit higher than sea level if it's flowing down into, let's say, a lake, for instance. Then as it's flowing in that lake, it might be another stream coming down on the other side that would take us down to sea level. But base level is quite simply the lowest level of that stream. Okay, well, that's it for the video. As always, good luck in the lessons, and we'll see you in the next video. So streams carry on two important processes. The first one is going to be erosion, and the second one is going to be transport. Now, erosion in this case is going to be breaking down stuff. Transport is going to be moving that stuff away. By erosion, we have three primary forces that go through this erosion. The first is going to be abrasion, and abrasion is quite simply knocking into stuff, okay? It's going to be moving stuff away, hitting it like that. Grinding is where you're going to be like using the particulate matter that's there to grind away at the bottom. And then dissolving would be dissolving away the minerals and things in the rocks that you can then carry away that way. As we transport, we have three different kinds. We'll have in solution, which is a dissolve load. Okay, we can see that one's kind of related here. We can have suspension, which is going to be that stuff that's carried in the water. So if you look at a muddy stream, the dirt that's being carried away that makes it kind of muddy, that's all in suspension. And then finally we have scooting or rolling along the bottom, and that's what we call the bed load, and that would just be the rocks that are tumbling along the bottom of the stream as it goes. Now, when we're talking about this, what we notice is there's two different kinds of things. We'll talk about competence, which is how large the particle can be. So the faster it's moving, the more force it has, the larger the particles that it can pick up and carry away in suspension. We also have capacity, which is how much it can actually carry. And that is also going to be determined by how fast it's going. Now, opposite to this carrying away stuff, we also have it putting it down, and that's what we call deposition. With deposition, we have a couple different things. The first we have is this alluvium, which we see, which is sorted materials, and it's sorted by size. As it's carrying away, when a stream slows down, the larger, heavier things are going to fall out of it first. So what we notice is if you take a look here in this canyon and they're showing this alluvium, and it's actually going to be kind of an alluvial fan, you'll notice that the larger boulders are going to be here, and as we travel away where it would slow down, you'll see that we see the smaller and smaller bits of materials being deposited. So alluvium is when it's sorted out by size. Now, as a stream deposits into an ocean or a lake, we're going to see a buildup of this alluvium here, and that's what's going to form a delta. So a lot of times what you'll see is if we have a river that's flowing down and it's hitting into the ocean, near the ocean, you can kind of see that it starts to triangular out like this. And that triangular shape goes back to the Greek letter delta, which capital is a triangle. But this is caused by this buildup of alluvium, and that'll split this river into several small little exitaries, not tributaries, but exitaries that will allow it to flow out to the ocean that way. And on the sides of this stream, what we'll see is a natural levees that are formed. And that's going to be when it flows a little bit faster because of flooding. You're going to see an accumulation of deposits on the banks that are going to go naturally this way. So we have natural levees, which are going to be the results of flooding, but then man will also build levees to kind of control these when they do start to flood. And we'll talk about that in the next slide. Now, the age of a stream or a river is going to determine the shape of its valley. If it's a younger stream and it's just cutting down to base level from the mountains, we're going to see that it forms this V-shaped valley. And you can see this V-shape really clearly here, where what we have is we have a faster moving stream that's going to quickly cut through and erode away the material, causing this deep V shape. As it gets closer to base level, we take away the gradient. It's going to move a little bit slower, and it's going to accumulate from the sides a little bit more, so its load's going to be a little bit larger. And what we end up with is a U-shaped valley, which we see kind of here. So we can see that the age is going to kind of make a difference. This V-shaped valley in time, given the ability to continue to flow, will eventually form into a U-shaped valley. Okay, so let's talk about floods and flood control. Floods quite simply means there's too much water. Okay, we have too much water flowing in the streams, and it causes it to overflow its banks. The causes for this naturally would be either heavy rains or rapid snowmelt. Both of those are natural ways to get more water into the stream beds and more than it can hold, so it causes it to overflow its banks, and that's how we get a flood. We can also see flooding as a result of development. If we start changing the streams, if we start rerouting the streams, if we start paving the lands over it, we're changing the natural part of the water cycle there. And what it's causing is you'll either have too much water running over the surface if it's paved into these banks or into these streams, and that'll cause them to flood. Or sometimes we'll change the bank and make it a channel instead. We'll make it lined with concrete, and then it can only hold a finite amount. So if we do that and then we get this additional runoff, that's how we can form flooding as well. Now, there's ways that we can talk about flood control. And flood control, quite simply, the way we deal with it is naturally you would have these levees. So if we have a stream and it's prone to flooding, then it's going to deposit sediment along its banks, and that's going to create kind of like an upper level bank. So the water, if it overflows, it'll hit those natural levees. If those aren't there, non-existent or not large enough, sometimes we'll create artificial levees, which means we'll go in and we'll build these artificial banks next to the stream. We can also create flood control dams. So upstream, we can build a dam with a large reservoir behind it. So if we have a lot of water flowing in, it'll collect here in the reservoir, and we can control the rate of flow flowing from it. And then also we could limit development. Instead of building a bunch of parking lots and paved roads and things next to the streams, we could leave it a little more natural, and that would allow water to go into the groundwater as opposed to surface water. Okay, so next we're going to talk about drainage basins. And drainage basins are quite simply just the term that's used for where a stream drains. So all of the water that's going to flow into a stream. So if we take our little simple model here and we have one stream that's coming down here, we'll notice that any water that's on the insides of these two peaks is going to trickle down into this stream, and that's how it'll find its way to the ocean. So for this stream here that we can kind of see right here is where the stream is, its drainage basin is going to be this entire area here. So it can be small, it can be a single valley draining into a single stream, or we can have large drainage basins. And perhaps one of the largest, and the largest in our country, is this one you see right here. And this here is going to be the Mississippi drainage basin. Okay, so that's it for our video. As always, good luck on the lessons, and we'll see you in the next video. In this unit, we're going to talk about what we call subsurface or groundwater. This is water that's in the ground. We've talked a little bit about surface water, and that would be like streams and runoff and things of that nature. But here, what we're talking about is the water that we find below the surface. And if we take a look here, you can see that there's a lot down here in the main water table. And this occurs in what we call the zone of saturation. And that's where the pores between the particles that we find in our soil is all going to be filled with water. Above that, we'll have a zone of aeration where those pores, instead of being filled with water, are going to be filled with air and gases. So we can see that we have this little differential line right here that separates our zone of aeration and our zone of saturation. Now we'll see a couple other things. We have our main water table here. We can have an elevated water table if we have what we call an aquitard below it. And that's just going to be a layer that doesn't allow water to travel through it. So it kind of traps that little bit of water, and that'll give us this perched water table. This perched water table will be like an elevated zone of saturation. Now, from there, we can flow water out to the surface via a spring, which we can see here, or it can actually leak out into the streams and things like that and drain back into the ocean that way. So let's take a look at some of the terms that we know about when we're talking about subsurface water. Now, the big three terms are going to be porosity. Porosity is a measurement of the percentage that is open space. So if I took a sample of soil and we have all of these large particles that are in here, porosity is going to be an estimate or a measurement of all of these little spaces between the particles. So that's what porosity is. Permeability, on the other hand, is the ability of a material to let water flow through it. So you could have a highly permeable substance which is very low in porosity or very high in porosity. The permeability is water flowing through it. The porosity is the amount of open space. And then the final term that we'd like to talk about is what we call an aquifer. And an aquifer are going to be layers that are highly permeable, which that means is most of the time when we're talking aquifer, we're talking that zone of saturation where we have all of this water that water can flow through, and that's where we can generally tap with our wells to get water from. Okay, so let's talk a little bit about springs, geysers, and wells. What a spring is quite simply it's an area where this groundwater meets the surface again. So if we notice in our top picture here, we have a lot of precipitation coming down, and that water is going to infiltrate or flow through these layers of rock until it hits some impermeable rock layer, or an aquitard we called it earlier. And that's going to allow a buildup of water. That water is also going to continue to want to drift downhill, so it's going to break through the surface here, and that's where we can have a contact spring. That's where the water is going to come out, and we see it that way. And you can see a lot of these in the desert when you're out hiking. You'll see these contact springs where you'll see a wet wall or something like that nature. And that's just because water's been able to trickle down. It hits this impermeable rock layer, and then it's forced to flow on top of that until it breaks through and is exposed to the surface again. Now we can have other kinds as well. We can have these artesian springs, okay, and that's going to be the same type of thing, but you have enough water that's coming down that it'll force that water to come out. So you can have a contact spring where it just drips through, or you can have an artesian spring where it seems to be coming out under force. Now, geysers are a little bit different. Geysers are going to be where you have these chambers, and most of the geysers are going to occur in areas that have volcanic activity. So you're going to have this heat flow down here, and it's going to heat up the rocks. And what happens is you're going to have water that's going to flow into these chambers here, and as it flows into these chambers, it's hot enough, it's going to cause it to start to boil. You're going to have other water flow in on top of it, and when you generate enough steam down here in the lower chambers, that steam's going to want to escape, and as it does so, it forces that water out of the geyser here. And you can see some pictures of this, or you could go on YouTube and find another video of like Old Faithful, which is a real famous geyser, and that's what we're talking about, is these chambers that build up pressure, and then they'll shoot out this water. And once that happens, you have more water that'll trickle into the chambers, and they repeat this cycle over and over again. And then finally, we have this concept of wells. And you can see them down here. Quite simply, what a well is going to do is it's going to tap down into this aquifer, this zone of saturation, and then we can pull the water out of that way. We can have a deep well here, we can have a slightly shallower well here, but the shallower well I wanted to show you is you can kind of see that there's this area here that we've pulled the water away from. Okay, and when we do that, that area, we call that a cone of depression, and you'll hear that in the lessons as well. Now, there are a couple threats on our groundwater. Probably the biggest threat is that we treat it as an endless source. We think we're never going to run out. And I have a picture over here of Hoover Dam, and you can see Lake Mead. And the reason that I showed you this is you can kind of see this white layer here that surrounds the lake. And that shows you where the water level is dropped in the last 20 years or so. So we're seeing from the mid-1990s to here, we're seeing a significant drop in the water level because we're using more than's being replenished every year, and we're realizing it's not an endless source. Now, the other major threat to it is contamination, and we can see contamination happening in several different ways. We have a well over here. If we have a septic tank that's broken or leaking here, then the contamination is going to come down and get into the groundwater and flow, and eventually it's going to reach down to where we're pulling that water back out. So it can be a septic tank, it could be a factory leak, it could be the big common one we're hearing now about fracking. But what we're doing is we're contaminating the groundwater. It's going to find its way into the aquifers, and then that's going to contaminate the water supply for us. So we have to take care of the groundwater because, like we said with the aquifer so many times, this is how we get our water to drink. Now, one of the most impressive geologic formations from groundwater is going to be these caverns. And you can see a picture of them over here, just these incredible underground caves that are like just a different world altogether. And the way they form is we'll see that we have water that's coming down, and that water will get into generally what we call limestone areas here. And those minerals that form the limestone are going to be soluble in water. So as that water is flowing through it, it's going to take away those minerals, and it's going to create these large empty pockets, which ultimately we'll call these caverns here. So you can see how they're formed just from the water going through and dissolving away the rock and taking it with it. Now, within the caverns, we'll see a couple different things. You'll see that we have stalactites. Now, the C in stalactite tells us that it grows on the ceiling, so these are the ones that are hanging. And then we have stalagmites. The G stands for ground, and that's going to be where it's building up from. And normally, we'll have a stalactite and a stalagmite right below it, and the way they form is as this water's coming through, it's going to evaporate a little bit and leave these minerals on the side of them. And as they do so, sometimes the water will drip down and we'll have the exact same process. It'll evaporate out and it'll build these mineral structures up. Now, when you have stalactite and stalagmites come together, and you can see it here, we form what we call a column. So these are kind of the neat things. They'll go to it in a little more detail, but if you have the chance to go and explore caverns, it's really an interesting experience. The last topic they're going to talk about in the unit is what we call karst topography. And karst topography is where you see this limestone down below and you have a lot of water flowing through it. And we're going to form these caves and caverns in here. But sometimes what happens is you'll have one and then this roof collapses. And as the roof collapses, we end up with what we call a sinkhole. Now, you can have a sinkhole as a depression. Part of it is collapsed down. You can have it as a hole, solitary hole leading into a larger chamber, or the entire chamber can collapse here. So when we talk about these karst topographies and these sinkholes, we're talking about areas like Florida where you see an awful lot of these large sinkholes that just spontaneously happen, and that's just where the roof over this cavern is collapsed down. Okay, so that's it for our video. As always, good luck in the lessons, and we'll see you in the next video.